Hey guys, this is Mr. Sal. We're going to look at a introduction to factoring polynomials. Thanks for watching. Don't forget to like, comment, and subscribe. The factoring stuff, we get the multiplication because I think we've seen it before. Hopefully we have. If we haven't, then this factoring stuff may be a little bit more difficult, which we expect because we haven't really seen it like this before. Okay. Factoring is the reverse of multiplication. It's not really the inverse of multiplication. That's the division part, which we talked about earlier. To factor a polynomial is to find an equivalent expression that is the product of polynomials, which we could include monomials as polynomials as well. An equivalent expression of this type is called a factorization of the polynomial. All right. Let's look at just factoring in general, okay? So if I were to look at factoring an expression, well, I don't know about expressions. No, yeah, let's take this even deeper into prime factorization, all right? All right, if we were to look at prime factorization, let's look at 42 on this game. So prime factorization, we would split this up using a factor tree, which we can still use when we're factoring this stuff out. And you notice it's even, so we know it's divisible by 2, and then 21, which is also factorable into 3 and 7. So 42, its prime factorization, 2, 3, and 7, would all be multiplied together to get 42. Now the only difference in this, with what we're going to be looking at least in the beginning, is the greatest common factor would be like having another term and then trying to figure out what the greatest common factor is. And that's the first step when we factor polynomials anyways. So if I were to look at 42 and compare it to, I don't know, let's just do 9 real quick. 9 splits up into 3 and 3, right? So if I wanted the greatest common factor between these two, well, I've got a 3 and a 3 that are common. So, in fact, that's all that's common. So it's also the greatest common factor. So between these two, I could factor out a 3, which we'll demonstrate with the binomial stuff, okay? So the greatest common factor is the term you get when you multiply all common factors from a set of terms, which we just kind of demonstrated. To factor it out, place the non-common factors in a set of parentheses and multiply the parentheses by the greatest common factor. That sounds really complicated, but hopefully it'll make sense when we look at some examples. Yeah, we're used to seeing distribution, which we've seen before, right? So I'd have 4 times x and then 4 times 3, which would give me this new expression. Factoring is just that backwards, okay? So, for example, the 5x, I can split that up between 5 and x. And then 30, I can split that up between 5 times 6. And I've got the greatest common factor, which is 5. So I'm going to pull that out of these two terms. And then what would I have left? The x and the positive 6. So that's how I get this factored term. Sometimes it's only factoring out numbers. Sometimes we only factor out letters. Sometimes we factor out both. Yeah, and we should, hopefully by the end of today, feel pretty comfortable doing either one of these. So let's start with this trinomial, 3 terms. And it is in descending order with degrees of 6, 4, and 3, which is great. And I'm just going to do this at its very most basic form, all right? So I'm going to take each of the 3 terms, 10x to the power of 6, 4x to the power of 4, and 3x to the power of 3. And I'm going to look at these individually, okay, because I want to see all the factors, which means I don't want exponents, okay? So that x to the power of 6, I know I'm going to have 6 of these x's being multiplied together. Now we'll see why this is important here in a moment. And not everyone needs this step, so if you don't need it, then, feel free to skip it, because you'll see a pattern, hopefully. But I still got that 10, right? So I'm going to look at the prime factorization of 10, which is 5 and 2. And my two prime factors on that, 10. So overall, this factors into 5 times 2 times 6x's. Okay. Now let's look at 4x to the power of 4. I know I've got those 4x's being multiplied together because that exponent of 4. But 4 just splits up into 2 and 2, which is nice. So that's 2 times 2 times the 4x's. Next up, I've got that 3, which is already prime, and then I've got 3 more x's. And you may be wondering why I kind of lined up the x's. I did that on purpose, right? Here's why. Is what I want first, just to begin with, is the greatest common factor, GCF. Is that something they put in TVs? I could be wrong. I don't know. Okay, just looking at this, okay. I see in this top term, the 10x to the power of 6, one of the factors is 5, okay. But the other two terms don't have a factor of 5, so it's not even common, all right. So the 5 is an uncommon term. The 2 is nice because the purple term, or factors, has a 2, but the green ones don't, which means it's not common. If it's common for 2 of them, and there's 3 terms, it's got to be common for all 3, all right? So what I notice for this next part, though, is I've got this set of x's, which are common, but it's only one factor for each, so it's only one x that's considered the greatest common factor on that, okay? Well, it's not just one x, I've got another one that's common, and then I've got another one that's common. So I've got 3 x's multiplied together, which is x to the power of 3. I do have other x's, but it's not common for all 3 terms, so it's not a common factor. What this means then is I've got this original trinomial, and I've got my greatest common factor, x to the power of 3, but I'm going to multiply it by the rest of what's left of those 3 terms. So I got my set of parentheses here, and should be addition for all 3 terms. Okay. All right, let's go back to the 10x to the power of 6, which I haven't read. So I've got 5 times 2, which is 10 still. And how many x's do I have left over? 3 of them. All right. Next up is the purple factors. 2 times 2 is 4. And on this one, I've only got the 1x. And finally, in green, there's only the 3 that remains right there. So it stays as the third term in the parentheses. And this right here is my factored out, my greatest common factor that's been factored out of this stuff, okay? Now we should consider some other things, but we're not going to worry about that until later, all right? Now we can't check this, okay? So, I mean, you could use the rectangle if you wanted to, but if you were to take that factored expression, if we were to take this and distribute the x to the power of 3 back into the parentheses, or use the rectangle, we need to get this same expression that we started out with, all right? That's not the answer. But we need to get that if we were to check our answer by redistributing that back into it. Now, does that guarantee that x to the power of 3 is the greatest common factor? Only if we've done our footwork in the beginning there correctly. Because if we've missed something, then it may turn back into that original expression, which will give you most of the points. But if you miss one of the common factors as part of the greatest common factor, then you'll still lose some points on the test. So let's look at these 3 terms individually, starting with the 15 x to the power of 6. And yeah, this is going to have 6 x's with it. So we got to look at that negative 15. and factor it out. Prime factorization, we've only got, well, we kind of have two choices on this. I got 3 and 5, but it's a negative value, right? So I'm just going to put the negative, I'm going to kind of separate it from the 3 and 5, or try to, just so I know that it's negative, okay? Because if a negative is common between all three terms, then we're going to pull that out as part of the greatest common factor. Next up, negative 5, x to the power of 4. So I've got my 4x's just to start out with. And I got negative 5, which is prime already. Next up, negative 5, x to the power of 3. So I've got my 3x's. And I got my negative 5 again. So I'm going to find my greatest common factor. And right off the bat, I can see that the negatives are common. So I know my greatest common factor is negative. What's another common factor in this? I heard 5. 5, yep. 5 is common amongst all three, so it's common. And then how many x's? 1, 2, 3. So negative 5 times x times x times x, which is negative 5 x to the power of 3. All right, so my original expression, I know I'm going to factor out a negative 5x to the power of 3. That's my greatest common factor. But then I got those three terms on the inside of that. Now we got to be careful on that last one. Everything was positive, so we just put in some plus signs. All right, we got to be careful on this one because we had some minuses and negatives. So I pulled out the negative 5x to the power of 3 from each of these. And my first term, negative 15x to the power of 6, I've got a 3. And then I've got 3x's, so x to the power of 3. In purple, all I've got is that x, and it's positive. And then for the green stuff, there's nothing left on that. However, we could just tack on a multiplied by 1 right there, just so we have something to show to take the space of that, its term, where that term was, okay? So now, this would be my final answer, by the way. And again, if you wanted to check, you could distribute this negative 5x to the power of 3 into the parentheses, or use the rectangle, and you should get the same expression that we started with. All right, factoring trinomials. This is like multiplying two binomials backwards. Now, those other situations were nice because we can factor out the greatest common factor. You should always see if there is a greatest common factor to factor out first before using this method. But we are going to take a trinomial and factor it out into two binomials, which we've kind of seen already, right? So, for example, let's do this with the multiplication stuff. So I would have two binomials like this right here. We'll just make these x's like this so it comes out neat. What numbers do you guys want? All right. So let's multiply these two. And I don't have enough space to use the rectangle. So I'm going to use, I'm not going to call it FOIL. Again, I'm going to call it distribution, where I've got to distribute the x into the other set of parentheses. So that's x times x plus 3 times x. And then I've got to distribute the 2 into the other set of parentheses as well. Now, the reason why I don't call this FOIL is because if one of these were a trinomial, then I don't know what they call it, okay, other than distribution. So I've got that 2 times x, positive, and then I've got the 2 times 3. So just simplifying this out, I've got x squared plus 3x plus 2x plus 6. And at this point, we would combine the 3x and 2x to be 5x. So I've got x squared, positive 5x, and a positive 6, which are my three terms, okay? Now, factoring the trinomial would be like starting with this x squared plus 5x plus 6, and then we ask you to factor it, okay? Well, how do we factor it? Well, it has to work backwards. So instead of this one kind of pointing to the 5x, it's going to split up. That 5x is going to split up into two separate terms, 3x and a positive 2x. The 3x is positive as well. So I haven't changed the value of the expression. All I did is I changed the 5x into a 3x and a 2x. Well, now I factor this. This is called factoring by grouping. I'm looking at this two terms at a time, okay? And I'm looking for the greatest common factor for both. In this first set, and I'm not going to show the work for it, just for the sake of time, and this is just an example, I can factor out an x from the x squared and the 3x. So what am I left with? I'd be left with an x and a positive 3. And then in this other set of parentheses, I can factor out, fix that, I can factor out a positive 2. Then what am I left with? An x and a positive 3. Now notice, the greatest common factors for both of these are being multiplied by the same binomial. That's crucial when we're factoring this stuff out, okay? Because what that means is that I can take the x plus 3's from both of these, and now it is a factor for two terms. I've got the green term, x times x plus 3, and then I've got the purple term, x times x plus 3, and the greatest common factor between these two is x plus 3. Well, then we know we just multiply it, the expression, by whatever was left over from the two terms, and that was the x and the positive 2. Well, it's in a different order, but see how we got the same thing from back here? So it not only works forwards, which we would consider the multiplying, but it works backwards with the factoring as well. The question really is, that 5x, how did we know to split it up into 3x and 2x? Because for the most part, we're not going to be able to see any of this stuff, right? So, yeah, how do we know to split these, what to split the 5x up into? And that's where the next slide comes in. So, once again, when factoring at all, we should always see if we can find the greatest common factor between the three terms, specifically for a trinomial. After we factored out the greatest common factor for this class, the leading coefficient will always be 1x squared, okay? Which makes that extremely convenient. Now again, that's after greatest common factor stuff. So our leading coefficient will be 1. This allows us to break this up the way that we want to, actually. Oh man, this is kind of a rule, actually. If we look at two factors of c that add up to b, then it's just x plus the one factor as the first binomial, and then the second binomial is x plus the second factor. So we'll make factor pairs of c, which includes the negatives, because sometimes that middle coefficient, the b value, is negative. And we may need negative factors of c. Then again, we find one pair whose sum is b, and then we replace those values into those two binomials, okay? So let's just consider that last example that we just barely looked at. So we know it has to factor into something x plus something and then x plus something else. If it were negatives, we would make it minus, x minus something in the binomials there, okay? So what we're saying on this is we want to make factor pairs of C. C in this case is the 6, because it's, well, C is kind of for constant on this. So factor pairs would be 1 times 6. But if I add 1 and 6, I get 7, not 5. So my other option is 2 and 3. Well, 2 plus 3 is 5, which is the middle coefficient, the middle term's coefficient. So in this case, since the coefficient of x to the power of 2 is 1, I just replace the 2 and 3 into the two binomials, and we can feel pretty good about that. Now why? Why does it end up being that way? Well, we just showed that with this other stuff, right? So we saw we can split this up, the 5x, into the 3x and the 2x. And then this is called factoring by grouping, where we factor out, we look at these as binomials again, two binomials. Then we factor out whatever the greatest common factor is for both binomials. This was x, that was 2. Then we factor out the greatest common factor for these two terms, which was x plus 3, a binomial. And we're left with the other binomial, x plus 2. So that's why this works. And you can do it over and over and over again. And the method would work the same. But as soon as we find those two factors for C that add up to the B term, or B coefficient, we can just replace those into these two binomials, okay? So on this one, we can look for a greatest common factor. However, the coefficient of that x squared is 1. So I know it can't be a number. And not all three terms have an x, so an x is not a greatest common factor either. So there's no common factors for these three terms, which means I can't factor anything out between the three. That's okay. So I have a coefficient of x to the power of 2, which is 1. So I'm going to look to the C value, which in this case is 48. And I want to list all of the factor pairs for 48. And I always like to start with 1 and 48, 1 and whatever the number is, because it's pretty easy, okay? But 1 plus 48 is not 14. It's 49. So what about 2 and 24? 2 plus 24 is 26, so that doesn't work. What about 3 and 16? No, it's getting closer, though. 3 plus 16 is 19. What about 4 and 12? 4 plus 12 is 16. No, but again, we're still getting pretty close. How about 6 and 8? Yeah, if I add these two together, I get 14. So my two binomials, which I can set up, that's a positive 6 and a positive 8. Done. Here's the good news about this problem is even if you did it wrong, it's likely that you'd get the right answer, but we check the work, so be careful on that, okay? So let's do this. Now, the C value on this is a negative 3. So, well, 3 is prime, so it's either 3 and negative 1, or it's negative 3 and positive 1, okay? But remember, I need to add these two together. What do I need when I add them together? I need it to be 9. Well, 3 plus negative 1 is positive 2, and negative 3 plus 1 is negative 2. Neither of these is 9, so it's just prime. Don't forget too, right, I should have done this, but we should have looked for a greatest common factor for all three terms in the beginning. But there's not an x in common, and the leading coefficient is 1, so no greatest common factor to factor out. You could factor out 1 if you wanted to. You just keep doing it forever, though. So we'll start. We should have done that last one. But is there any greatest common factors for any of these three? No. There's not a z in common, and again, that leading coefficient is 1, which is nice. That is what makes this so that we can just look at our two final binomials to start out with the z's, okay? So I'm looking at the c value, 21, and again, 1 and 21. If I add those together, I get 22, which is not negative 10. And, well, 2 is not going to work. We got to use a 3 on that, right? 3 and 7. Now, here's the problem with 3 and 7. If I add them together, I get positive 10, right? So this is where I got to look at the negative factors as well. Negative 1 times negative 21 is positive 21, which is what this is, positive 21. But if I add those together, I get negative 22. That's no good. So let's try negative 3 and negative 7. Well, if I add those two together, then I get negative 10, which is what I want, because that's my b value. So, once again, I just plug these in to my two binomials. And that is all. And here's why it doesn't matter, is because, if I were to use the FOIL method or distribution or the rectangle stuff to expand this and then simplify it, I would still get z squared minus 10z plus 21. So for me, the order of them doesn't matter. I don't know any professors where it does either. I could be wrong, though. Now, just so you guys know on this one, just to start out, that sometimes that 1 isn't shown right there. Maybe it helps you, maybe it doesn't. In any case, if it does help you, then show it, okay? I don't really have a rule for this one, actually, that I can think of right off the bat. So let's do this one together. There's no greatest common factor for these three terms. There's no x's in common, no y's in common for all three. And I've got two coefficients that are 1, but again, factoring out a 1 isn't going to do anything for us. So it looks like we may have to look at that factoring by grouping stuff on this. All right, so in any case, I'm looking at this negative 30, and I'm not worried about the y squared, okay, because we're looking at factoring by grouping in this case, which we've seen already. And I want two factors of negative 30 that will add to 1. So 1 and negative 30, that's no good. Neither is negative 1 and positive 30, that's no good. What about 2 and negative 15? Nope, that's negative 13. So negative 2 and 15, that's positive 13. What about 3 and negative 10? That closer, negative 7. Negative 3 and positive 10, positive 7. All right. 4 doesn't work, but 5 and 6 would. What about 5 and negative 6? Nope. Those would add to negative 1. So what about negative 5 and positive 6? Yeah, these will add to positive 1. So what this means then is I've got to take that 1xy and separate it into negative 5xy's and positive 6xy's. Let's rewrite this one, okay? All right. So this 1xy, again, I'm splitting it. The 2 will add up to the 1xy. And again, the good thing is that they're also factors of that negative 30. So that's a negative 5xy. And then the positive 6xy. And it wouldn't matter which order you put these in, okay? So I could put the 6xy first and the negative 5xy second. It's not going to matter. I still got that x squared and the negative 30 y squared. Okay. So again, I'm looking at these as two separate binomials. And we can look at these over here. So I've got x squared minus 5xy. And, well, I'm going to expand that x squared. So the only factors that are common between these two are the x's. I'll do it in green. These x's. So its greatest common factor is an x. And then we have what was left over, the x. And then the negative 5y. Right there. All right, then we got the 6xy minus 30y y squared, but again, I'm going to show the two y's on this. And I'm going to factor that negative 30 using the two factors we had used before. So that's 6xy minus 5 times 6 times y. And I'm looking for common factors like 6's. And then I've also got a set of y's that are common factors. So our greatest common factor is 6y. And that's a positive 6y right there. And then what do I got left over? Goes in the parentheses. I got that x from my leading term there. And then I've also got the negative 5 and the y. So it's just repeating the greatest common factor stuff on that. But we can see inside the green parentheses and the purple parentheses, I've got x minus 5y again, which means I can factor those out as x minus 5y as the greatest common factor between the two terms now. And then what do I got left over? The greatest common factors from those, which was x, and then the positive 6y right there. And this is the term we wanted. So I guess that's a very limited usage rule on this one, right? We could have said, well, I'm going to separate this into two binomials with x's and y's, like this. Then I had a negative 5 and a positive 6 of them. That seems like a rule, but it may be hard to identify this, and it may get mixed up with the other rules. So be very careful if you think of this as a rule. All right, so on this one, our leading coefficient is 3 now. So we should certainly look for some kind of greatest common factor for this one. So let's look at these. So I got my first term, 3w to the power of 2, which would be 3 times 2w's, because 3 is already prime. That's nice. 48w. Let's see, 6 and 8. So I'm going to split it up into, we'll say 6 and 8. That's okay. So that's 2 and 3. And then 8 is 2 and 4, which is 2 and 2. So it's prime factorization. 2 times 3 times 2 times 2 times 2. And then times the w. Then we also got the 180, just the constant itself. So let's see, 180. I'm going to split it up into, we'll say 2 and 90. What the heck? Then I got 45 and 2. And 45 is 9 and 5. And 9 is 3 and 3. So the final prime factorization is 2 times 3 times 3 times 5 times 2. Okay, so I'm looking for any common factors which will be a part of the greatest common factor. Oh, I've just got kind of a set of 3's right here like this. So our greatest common factor is just 3. So from this 3w squared plus 48w plus 180, I know that I can factor out a 3 from this, which leaves me then with, that's a w squared, first term, and then that's a positive 2 times 2 times 2 times 2, 2, 4, 8, 16, w, and then the green stuff, still positive, 2 times 3 times 5 times 2 is 60. All right, so I have this new expression with the greatest common factor taken out. So I'm just going to get rid of this other stuff for now so we can focus on it, okay? And I'm going to forget about the 3 for now, just knowing that it's going to come back, okay? Because the coefficient of w squared is a 1. So that means that this trinomial should factor, it may factor into two binomials like this. But again, we should never forget that that greatest common factor of 3 was pulled out already, okay? So I'm looking at the 60, and I need two factors of 60 to add up to 16. And yes, I'm going to do this long and painful, not as a torture technique, but just so we can see the method, all right? 1 and 60, no good. That'd be 61. 2 and 30, nope, still no good. 3 and 10, no. Did I miss something on there? 3, oh, that's 3 and 20. 3 and 20, nope, 23, that's no good. What about 4 and 15? That's 19, so we're getting closer. 5 and 12, nope, 17. 6 and 10, yep, that'll do it. 6 plus 10 is the b value at 16. Again, I'm looking at the b value for our greatest common factored expression. So, since that is 16, the two factors were 6 and 10, positive 6, positive 10, done. Is this factorable? Well, that's a coefficient of x squared that's 1. So we can go right into our method of looking for factors of c. 1 and 15. What about 3 and 5? No. Negative 1 and negative 15? Nope, that's no good. What about negative 3 and negative 5? Now this is where the mistake happens sometimes is, sometimes we'll say, well, 3 and negative 5. Well, that's a positive 15 value of c right there. 3 times negative 5 is negative 15, so it's a negative 3. And these are all the factor pairs of positive 15. So is it factorable? Nope, it is not.